Hello everyone. Welcome back to the channel. Every search, every online payment, every AI response, and every video you stream depends on data centers. But have you ever wondered how these massive facilities stay cool when thousands of powerful servers generate incredible amounts of heat? Today, we'll explore the engineering behind air-cooled data centers and discover how fans, chilled water, and precision cooling systems work together to protect the digital world. Let's begin. Imagine this. A single room consumes more electricity than an entire neighborhood. Inside this room, artificial intelligence is learning. Banks are processing millions of financial transactions. Hospitals are retrieving critical patient records. Businesses are operating 24 hours a day. And millions of people are streaming videos, searching the internet, and talking to intelligent assistants. To everyone outside, everything feels instant, invisible, effortless, but hidden behind every click, every search, every payment, and every AI response is one invisible enemy. Heat. Every server, every processor, every memory module, every network switch consumes electrical energy, and almost 100% of that electrical energy becomes heat. Not some of it, not most of it, almost every single watt. Now imagine the cooling system suddenly stops. Not tomorrow, not an hour from now, right now. Within minutes, temperatures begin to rise, cooling alarms activate, servers automatically reduce their performance to protect themselves. Applications begin slowing down. Users start experiencing delays. If the temperature continues rising, entire server clusters can shut down. Cloud services become unavailable. Financial transactions stop. Critical business operations are interrupted, and millions of people feel the impact. Not because the servers failed, but because the cooling failed. That's why, inside every modern data center, cooling is never considered a supporting system. It is mission critical. Today, you are the HVAC design engineer. Your client has given you a challenge. Design the cooling system for an 8-megawatt data hall. Choose equipment. That is too small, and the servers overheat. Choose equipment. That is too large, and millions of dollars are wasted. So how do engineers determine the exact cooling capacity a data center requires? The answer begins with one simple question. Where is the heat coming from? Many people believe cooling means producing cold air. It doesn't. Cooling is simply the process of removing heat. That single idea changes everything. Before engineers select chillers, before they size pumps, before they choose fan wall units, before they draw a single HVAC layout, they first identify every source of heat. Because if you know exactly where the heat is generated, you can calculate exactly how much cooling is required. Everything that follows, the pipes, the pumps, the chilled water system, the fan wall units, the control valves, and the chillers, is simply the result of one engineering calculation. Heat in must always equal heat out. Nothing more, nothing less. And that simple principle is the foundation of every reliable mission-critical cooling system. In the next chapter, we'll step inside our 8-megawatt data hall and begin calculating where every single watt of heat comes from. Now, let's step inside the facility. This is a modern, hyperscale data hall designed to support high-density computing, cloud services, and the rapidly growing demands of artificial intelligence. The room itself is surprisingly simple. 72 meters long, 48 meters wide, 6 meters high. But don't let the empty space fool you. Every square meter has been carefully planned to maximize reliability, airflow, and cooling efficiency. Inside the room, there are 400 server racks. Each rack consumes 20 kilowatts of electrical power. At first, 20 kilowatts may not sound extraordinary, but when you multiply that figure by 400 racks, the numbers become astonishing. Let's calculate it together. 400 multiplied by 20 equals 8,000 kilowatts, or simply 8 megawatts. That is our total IT load. And here's something remarkable. That single calculation already represents almost the entire cooling challenge inside the data hall. Because unlike an office building, where cooling must account for people, lighting, and solar heat gain, a data center's different. Here, the servers dominate everything. Almost every watt consumed by the equipment is eventually released as heat, which means our 8 megawatt electrical load very quickly becomes an 8 megawatt cooling problem. But engineering never stops at the largest number. Professional designers know that ignoring the smaller heat sources can lead to inaccurate equipment selection, reduced efficiency, and unnecessary operating costs. So before we size a single cooling unit, we must account for every source of heat entering the room. Let's begin with the obvious one, the IT equipment. 400 racks, consuming 8,000 kilowatts. This is, by far, the largest contributor. Next, the lighting. Modern LED fixtures are extremely efficient, but efficiency does not eliminate heat. Eventually, almost all of the electrical energy used by the lighting also becomes heat. For this project, the lighting contributes 35 kilowatts. Now, let's include the people. A data hall is not continuously occupied. Most of the time, it operates automatically. But engineers, maintenance technicians, and commissioning teams still enter the room. Let's assume 10 people are working inside. Each person generates approximately 100 watts of sensible heat. Together, they contribute 1 kilowatt. Compared to the IT load, that number seems tiny. But engineering is the science of accounting for every watt. Next, the building itself. Even with excellent insulation, heat continuously enters through the roof, the walls, the floor, the doors, and cable penetrations. This is known as the building heat gain. For our project, we'll assume 90 kilowatts. Finally, there is fresh outside air. Data centers require controlled ventilation to maintain indoor air quality and positive building pressure. But outside air always carries heat. Before it enters the room, that heat must also be removed. For our design, the ventilation load contributes 180 kilowatts. Now let's calculate our total cooling load. IT equipment, 8,000 kilowatts. Lighting, 35 kilowatts. People, 1 kilowatt. Building heat gain, 90 kilowatts. Fresh outside air, 180 kilowatts. Add them together, and the result is 8,306 kilowatts, or approximately 8.3 megawatts. That is the actual amount of heat our cooling system must continuously remove. Every second, every minute, every hour, without interruption. But are we ready to select our cooling equipment? Not yet, because experienced engineers never design for perfect conditions. And that's exactly what we'll explore in the next chapter. At this point, we know our total cooling load, 8,306 kilowatts. So, should we simply select cooling equipment rated for exactly 8,306 kilowatts? Absolutely not, because engineering is never based on perfect conditions. Real buildings don't operate inside a laboratory. Outdoor temperatures change, humidity changes, air filters become dirty, heat exchangers slowly lose efficiency, control valves drift, sensors become less accurate, and perhaps most importantly, the client's business continues to grow. A data hall that is designed for today's servers may need to support more powerful hardware just a few years from now. Good engineers don't design only for today. They design for tomorrow. That's why we include a design safety margin. For this project, we'll use 8%. Let's calculate it. 8,306 multiplied by 1.08 equals 8,970 kilowatts. Rounded, our design cooling capacity becomes 9 megawatts. Now, and only now, are we ready to select our cooling equipment? The first equipment inside the data hall is the fan wall unit. Its job is straightforward. Draw hot air from the hot aisle, pass that air through chilled water cooling coils, remove the heat, and deliver cooled air back to the cold aisle. This process repeats every second of every day. For our design, each fan wall unit provides 300 kilowatts of sensible cooling. Now, let's determine how many units we need. Our required cooling capacity is 9,000 kilowatts. 9,000 divided by 300 equals 30. At first glance, the answer appears simple. Install 30 fan wall units. But this isn't an office building. This, a mission-critical data center. Cooling must never stop. Imagine one fan wall unit unexpectedly fails. Without spare capacity, the remaining units would immediately become overloaded. Temperatures would begin rising, and the risk to the servers would increase. That's why mission-critical facilities are designed using N+1 redundancy. The calculation is simple. 30 units carry the full cooling load. One additional unit remains available as a standby. If any operating unit is removed for maintenance or experiences an unexpected fault, the standby unit immediately takes over. No interruption, no overheating, no downtime. To everyone outside the building, nothing appears to have changed. But inside, the cooling system has quietly protected the entire data hall. That is engineered reliability. So our final selection becomes 30 operating fan wall units plus one standby unit, a total of 31 fan wall units. This is not oversized equipment. It is carefully engineered resilience. Now we've selected the indoor cooling equipment, but one important question still remains. Where does all that heat actually go? Because removing heat from the servers is only half the journey. The heat still has to leave the building, and that's where the chiller plant takes over. Now that we've selected our cooling equipment, let's follow the journey of heat itself. It all begins inside the server. Every processor, every memory module, every graphics processor, and every power supply consumes electrical energy. And almost every watt of that electrical energy becomes heat. That heat is released into the air, flowing through the server. By the time the air leaves the rear of the rack, its temperature has increased to approximately 40 degrees Celsius. Now, the fan wall units take over. Large, high-efficiency fans draw the hot air through chilled water cooling coils. Inside those coils, something remarkable happens. The air never mixes with the chilled water. Instead, the heat passes through the metal walls of the cooling coil. The chilled water absorbs the heat. The air temperature falls to approximately 18 degrees Celsius. That cooled air returns to the cold aisle. The servers draw it back in, and the entire cycle begins again, second after second after second, 24 hours a day, 365 days a year, without stopping. But the journey isn't over yet. The chilled water has now become warm. It carries all the heat removed from the servers. That warm water leaves the data hall and travels to the central chiller plant. The chiller plant is the heart of the cooling system. Its purpose is simple. Take the heat collected inside the building and reject it to the outside atmosphere. For our project, our required cooling capacity is 9 megawatts. Each air-cooled chiller can remove 1.5 megawatts. Let's calculate how many chillers we need. 9 divided by 1.5 equals 6. So, is our answer 6 chillers? Not quite, because once again, this is a mission-critical facility. If one chiller is shut down for maintenance or experiences an unexpected fault, the data hall must continue operating without interruption. So once again, we apply N+1 redundancy. 6 chillers operate continuously. 1 additional chiller remains available as a standby. Our final selection becomes 7 air-cooled chillers. This ensures the required cooling capacity remains available even if 1 chiller is unavailable. Reliability is never an accident. It is engineered. When most people look at a data center, they see rows of computers. Engineers see something completely different. They see heat, airflow, pressure, water flow, control systems, redundancy, reliability, because a data center isn't simply a room full of servers. It's a carefully engineered ecosystem where every component depends on every other component. The servers depend on electrical power. The electrical system depends on backup generators. And the entire facility depends on cooling. Because without cooling, there is no artificial intelligence, no cloud computing, no online banking, no video streaming, no digital healthcare, no instant communication. Every email you send, every online payment you make, every AI response you receive depends on someone, somewhere, carefully calculating how to remove every single watt of heat. And it all begins with one simple question. Where is the heat coming from? Thank you for watching. If you enjoyed this engineering documentary, consider subscribing for more videos on HVAC engineering, mission-critical cooling, data centers, and the engineering systems quietly powering our digital world. I'll see you in the next one.